Good day, learners. This is Dr. B. Brailson Mansingh, Assistant Professor in the Department of Mechanical Engineering, Sri Ramakrishna Engineering College, Coimbatore. Today I welcome you all to this session on velocity analysis in mechanisms, a subtopic of kinematics of machinery, which falls under theory of machines. To understand this topic, learners must have a prerequisite knowledge on engineering mechanics, engineering graphics and basics of mechanisms like what's a link, linkage, types of mechanisms, etc. Now let's move into this topic. Being velocity analysis, let's go from the scratch in the case of velocity. First thing is displacement. So looking at the first figure, a person moves from A to B, that is, the person is displaced by a distance del x from A to B. So we never worry about at what speed they have gone from A to B and at what time they have taken to move from A to B. So it is just a distance between A and B, which is del x. This is what is displacement. Coming to the next point, velocity. A car moves by the same distance del x, but here we are worried about at what time it has taken to move from A to B and what is the direction, because velocity is a scalar. So we are worried about the direction as well as at what time it has taken to move from A to B through a distance del x. So the rate of change of displacement del x with respect to time is velocity. Again, this velocity has two types. One is linear velocity, another one is angular velocity. The case what we have seen in the case of car, this is a linear velocity because the object whose velocity is being measured moves linearly. Coming to the third figure, where you can see a circle, that's the path of a particle. Let us assume that the particle moves in a circular path shown in figure, and in this case the particle will have angular velocity omega. So there were two types of velocity, one is linear velocity in the case of car and angular velocity, which is the case of the particle moving in a circular path. There is a relation between linear velocity and angular velocity which is very important in understanding the analysis of velocity analysis of mechanisms. So let us consider this third figure where a particle moves in a circular path with the angular velocity omega. Let us consider a portion where a particle moves from A to B whose distance is s and the angular displacement is theta. Let the path has a radius of r. The distance s, angular displacement theta and radius r can be related using the basic physics relation called the sector length relation as s equal to r into theta. So this sector length formula is used to relate the linear velocity with the angular velocity. Now let's come to the basic definition of velocity. It is rate of change of displacement. Here in this case displacement is s. Distance between A to B is taken as s. So rate of change of displacement s divided by time. Because it is velocity, we need to consider the time as well. Now inserting the sector length relation in this velocity formula, instead of s it can be replaced by r into theta, where r is the radius of the path and theta is the angular displacement. Again, looking into this case in depth, r does not vary with time because even though the particle moves through a 360 degree, the radius remains constant and it doesn't vary with respect to time, whereas theta varies with respect to time. So r is a constant within this case, so it can be taken out and the remaining is d theta by dt. So as we know, it is rate of change of angular displacement by time, which is angular velocity omega. So the linear velocity can be related to angular velocity as v equal to r into omega, where omega is the angular velocity and r is the radius of the circular path. So this relation is very important in making velocity analysis in mechanisms. Let us consider this 4-bar mechanism. If you have come across the types of mechanisms, this is the very first and very important mechanism which has many applications even today. Now let us take this 4-bar mechanism where the link AD is fixed and link AB makes a complete 360-degree rotation in the clockwise direction, and its speed is given as 120 rpm, and link BC and CD oscillates and makes a partial rotational motion. As a whole, the link AD is fixed and other links either make full rotation, that is like AB, and other links BC and CD make partial oscillatory motion, right. So as you can see in this figure, the link, the point B makes a complete 360-degree rotation and makes a circular path. This is given for your better understanding, whereas the point C makes a arc form which translates to and forth, so that both the links BC and CD will oscillate. Now with this understanding, we will start making velocity analysis. Here in the case of this mechanism, all these velocities will be represented as relative velocities. For example, if I talk about velocity of B, I will talk with respect to A or with respect to C. Both are relative. If the link is fixed, it becomes absolute velocity. If the link is in motion, then it becomes relative velocity. For example, if I talk about the velocity of B with respect to A, then it is absolute velocity because the point A is fixed. But at the same time, if I talk about B with respect to C, then it is a relative velocity with respect to C because C also moves, right. So here whatever we speak is about relative velocity, and if the reference link is fixed, it becomes absolute velocity. So in general, it is relative velocity. Now let us start with a fixed link. The link AD is fixed. Okay. So the velocity of D with respect to A or A with respect to D is always 0 because it does not move with respect to each other. That is what is mentioned as velocity of D with respect to A equal to 0 meter per second. Now we have some data related to link AB, but it is not directly or explicitly given. The speed of the link is given in terms of RPM, 120 RPM. We need to convert this data into usable linear velocity because the velocity diagram is drawn completely based on linear velocity. So any data need to be converted to linear velocity to be used in velocity diagram. Similar is the case with vice versa as well. Any data that is taken from velocity diagram need to be reworked for useful purpose. So the to and forth work need to be done parallelly. Now coming to this link AB, we will say as, let us say velocity of B with respect to A. Since A is fixed, it is convenient for me to express B with respect to A. Now the speed given in RPM can be converted to angular velocity using the relation 2 pi nBA divided by 60. The common general formula omega equal to 2 pi n by 60 has been fixed to the link AB. Now using the linear angular velocity relation or using this or fitting this linear angular velocity relation to this link AB, it is velocity of B with respect to A is equal to radius. What do you mean by this radius? As far as this concept is concerned, it is the length of the link AB. you can refer to this figure where the point B makes a circular path where the link BA becomes the radius of the circular path. So, instead of R, the length of link AB can be used, and the next omega is angular velocity of the link AB, which we have obtained from the 120 RPM, and the linear velocity of link B with respect to A is calculated as 0.5 meter per second. So, in this mechanism, as of now, we have the velocity of two links. One is velocity of D with respect to A, that is velocity of AD. Another one is velocity of B with respect to A. Velocity of D with respect to A is 0 because it is completely fixed, and velocity of B with respect to A has been computed based on the given data of 120 RPM, which rotates in the clockwise direction. Now, speaking about velocity, it is a vector quantity, so direction is also very important. As of now, we need not worry about the direction of AD because the velocity is 0, it does not move. Coming to the link AB, it has a direction, it is a vector quantity, it has a magnitude. Now, that need to be fixed. Now, let us consider the same figure where you can consider this figure, a particle moves in the circular path, right, which is same as the link AB where the point B makes a circular path, right. So, for such a case, the linear velocity is always tangential to the circle. That means it is tangential to this point and makes 90 degree with the link. This is what is the case. So, implementing this concept to this link AB in this mechanism, this velocity of B with respect to A acts perpendicular to the link AB and tangential to the circle drawn through B with A as center. Okay. So, direction of B with respect to A is fixed, whereas there is no direction for AD since it is 0. We will start drawing the velocity diagram. Now, the thing is, velocity of D with respect to A is 0, velocity of D with respect to A is 0, and velocity of B with respect to A is 0.5 meters per second. Additionally, I have a direction as well for velocity of B with respect to A. Now, since velocity of D with respect to A is 0, it makes a single point in the velocity diagram, because the length of any line in the velocity diagram represents the magnitude of velocity. Since velocity of D with respect to A is 0, it does not make a line, it makes a single point in the velocity diagram. Once again I repeat, the link AD makes a single point in the velocity diagram. The reason is the velocity of D with respect to A in the velocity diagram is 0. Since the length of any line in the velocity diagram represents the magnitude of velocity, since the magnitude of velocity of D with respect to A is 0, it cannot make a line in the velocity diagram, it will make a point in the velocity diagram, and the same point takes the name as A comma D. Now, coming to the link BA or AB. So, the velocity of B with respect to A need to be represented in the velocity diagram. We know its magnitude 0.5 meter per second. We know its direction, which is shown in the space diagram. So, the length of the line need to be 0.5 meter per second and the direction must be this one. Okay. you have to use appropriate scale as per the space available in your drawing sheet or drawing note, and from A draw a line parallel to this direction, that is VBA, from point A in the velocity diagram, right. So, the length must be the length of the line AB in the velocity diagram, the length of the line AB in the velocity diagram must be equal to 0.5 meter per second converted to appropriate scale, and it must be parallel to this vector VBA, or it must be perpendicular to the link BA. So, the velocity of D with respect to A and B with respect to A has been represented in the velocity diagram. Then two more links exist, velocity of C with respect to B and velocity of C with respect to D. You can ask, why can't we say that velocity of B with respect to C? Both the cases will give me relative velocity. Okay. Similarly, why I say that velocity of C with respect to D is, it is convenient for me to always refer any point of velocity with respect to a fixed point. Since D is fixed, I refer the velocity of link CD as velocity of C with respect to D. Now, coming to these two links BC and CD, both make oscillatory motion. The motions were neither completely rotational not linear, but any point on both the links make a rotational motion, but it is not a complete rotational motion, a partial rotational motion. So, it cannot be taken as linear velocity, it need to be taken as a angular velocity. It exhibits only angular velocity, it does not exhibit linear velocity. So, as we have seen here, if a particle has angular velocity, its linear velocity will act tangential to the path or perpendicular to the link, tangential to the path or perpendicular to the link. Now, using the same concept as we have used for BA, from B in the velocity diagram, draw a line perpendicular to the link BC in the space diagram. Similarly, from D in the velocity diagram, to represent the velocity of CD, draw a line perpendicular to link CD in the velocity diagram. Both will meet at point C. Now, the velocity diagram is closed. Now, link DC in the velocity diagram represents the velocity of link CD, and link CB in the velocity diagram represents the velocity of link BC. The data in the velocity diagram represents the linear velocity, right. All the velocity diagram represents the linear velocity, and we have to use the linear and angular velocity relation to convert back and forth. Now, the complete velocity diagram has been drawn. For example, I need to know the velocity of link CD. It's simple, just measure the length of line in the velocity diagram of link CD and convert it to appropriate scale. You will get the velocity of link CD. The velocity what you get is always linear velocity. Understand that it is after scale conversion. Each one will be using your own scale. As far as the scale is bigger, or in further simple words, as far as your velocity diagram is bigger, your results will be accurate. As far as your velocity diagram is smaller, your results will be approximate. So, use the maximum scale so that depends on the space you have, and depending on the space availability, opt for the maximum scale so that you will get more accurate results. Now, the velocity of CD can be directly measured from the velocity diagram of length CD or DC, so that After scale conversion, you will get the value as 0.385 meter per second. And this is the linear velocity. If you want angular velocity, we have to do the similar process what we have done for link BA, where there what we have done is RPM has been converted to radians per second and radians per second has been converted to meter per second. Here we have things in meter per second. The reverse process need to be done. What we need to do, use the velocity, linear velocity angular velocity relation, apply it to the link CD so that you can get the angular velocity. VCD is obtained from the velocity diagram, CD can be obtained from the space diagram. You can calculate the omega CD in radians per second. Similarly, the same thing can be done for the link CB as well. So this is how to make velocity analysis in any simple mechanism. So with this discussion, we'll wind up this session. I hope you have had a better understanding as well. Happy learning to all. Thank you for your patient listening. Thank you.